Good afternoon, student. Good afternoon. Yesterday, we have discussed, I think, a problem on super mesh, right? The super mesh analysis. So everybody got the answers for the super mesh analysis problem that we have discussed yesterday. Please respond. Any difficulty is there in that problem, what we have discussed in the last class? So that is already here on the presentation. A super mesh means any current source. If any current source is there between any two loops, then we will combine those two loops and we will form a mesh which is known as super mesh, and then we will apply the KVL equations. Okay, so everyone got the answers here. I1 has I1 19.99 amperes, I2 17.33, I3 is 15.33. Everybody got the answers? Please respond. You got the answers or not? Yes. Okay. So, right. Okay. So now,
Yes, sir.
yeah. Right. Very good. So now we'll discuss one more problem on the super mesh analysis. Suppose if the current source is present at the boundary, that means at the peripheral of any circuit, means a boundary of the given circuit. Okay, it is also a super mesh problem only, but a slight variation is there with the previous problem and this one. That means just we will have a current source at the boundary of the circuit, right? Okay, note down this circuit. This is also related to the super mesh, but the current source is at the boundary. Right? Find the currents in the circuit. Find the mesh currents for a given circuit. Is it visible, the circuit?
Yes, sir.
Yeah, okay. So how to form a super mesh here? So what is the first step to be followed here to solve the problem? To find the mesh currents, what is the first step we need to follow? So first assign the currents. Apply currents all for all the meshes in clockwise direction. Okay. So since here three meshes are there, we'll solve. The first one is I1, second one I2, and third one is I3. Okay. So right, if we know that there is a current source, so as per the super mesh analysis, so we can neglect this one. So neglect this outer loop. No need to consider. As per the super mesh analysis concept, we can neglect this loop. So that means apply KVL for only the loop 2, that is which contains I2, and the loop 3, which consists of the current I3. So apply KVL to the two loops only, because the outermost loop contains supermesh analysis. So we can neglect the branch which consists of the current source in evaluating the mesh currents. So apply KVL to only the two equations, that is the second equation and that means second loop and the third loop. Okay, so write the KVL. What is the KVL equation? If you apply for second equation, second loop, how to apply KVL for second loop? Start with the 3 ohms minus 3 into what is the current flowing through 3 ohms? Current through 3 ohms is I2 minus I1. I2 minus I1 minus 10 volts minus 2 into I2 minus I3. I2 minus I3 is equals to 0. So simplify this. Minus 3I2 plus 3I1 minus 2I2 plus 2I3 is equals to 10 volts. So 3I1 minus 5I2 plus 2I3 is equals to 10. This is the one equation. 3I1 minus 5I2 plus 2I3 is equals to 10. Right. Now apply KVL for the third one, the loop which consists of the current I3. Apply KVL for the loop with the current I3. So plus 10 volts minus I3 minus 2 into I3 minus I2 is equals to 0. So minus I3 minus 2I3 plus 2I2 is equals to minus 10. Right? 2I2 minus 3I3 is equals to minus 10. 2I2 minus 3I3 is equals to minus 10. So what is I1 value from the first loop? So as per supermesh analysis, we have neglected the first one, but we will get a relation from that supermesh, from the current source. What is I1 value from the first source, first loop? I1 and that 10 amperes current source, both are in same direction. So what is I1 value? From the first loop. So since I1 and 10 amperes are in the same direction, there is no other current. So from the first loop, we can write I1 is 10 amperes. I1 is 10. So substitute the 10 in this equation 1 here. So then we will have two equations with the two unknowns, I2 and I3 only. If I1 is 10 amperes, so from the first equation, 10, I1 10, so 30 minus 5I2 plus 2I3 is equals to 10. So minus 5I2 plus 2I3 is equals to, so 10 minus 30. So this is minus 20. And second equation is 2I2 minus 3I3 is equals to minus 10. So solve these two equations to find out I2 and I3 values. Whereas I1 is 10 ohms. I1 value is 10. Solve these two equations for I2 and I3 values. So that is multiply this with 2, this with minus 5. So minus 10 I1 plus 4 I3 is equals to minus 40. Minus 10 this is I2, minus 10 I2 plus 15 I3 is equals to plus 50. Right. Plus minus 11 I3 is equals to minus 90. So I3 is 90 by 11. 90 divided by 11. What is this value? I3? Are you following? Are you solving this problem? Yes, Sai Sandhi. 8.90 divided by 11 is 8.18, right?
8.18, sir.
Yeah, right. 8.18 amperes. I3 is 8.18 amperes, I3. So now find I2 from this equation. Find I2. Already we know one relation, 2 I2 minus 3 I3 is equals to minus 10. So 2 I2 is equals to minus 10 plus 3 into 8.18. So minus 10 plus 3 into 8.18. Yes. Somebody have posted? No. It is I2 value after simplification. I2 7 amperes, right? Is it the answer you got? I2 is 7.27. I2 value.
Yes, sir.
Yeah, right. I2 is 7.27 ampere. So now we have I3 8.18 amperes, right? So only there is a slight difference if current source is present at any boundary. If that means a outer loop, means if current presents in the outer loop, so simply neglect that loop. That means remove that loop and apply the KVL equation for the remaining loops and find the currents. So from that loop where we neglected the current source, we'll get a relation in unknown currents. So use that current, that relation to solve the unknown currents, right? So mesh analysis we have used to solve a network which consists of large number of voltage sources compared to the current. So that is to find out, particularly to find out the mesh currents. Mesh currents, we use the mesh analysis. In that a variation of in mesh analysis is if any loop consists of the current source in between any loops, then we'll modify that mesh analysis as a super mesh. So that means we formed a super mesh by combining the loops which is having a current source between them. If any two loops are having current sources, then we removed that current source and we applied the super mesh analysis, and we solved some problems for super mesh also. So is it clear, the mesh and super mesh analysis in solving the networks? Any doubts in that? Any difficulty in solving the network using mesh or super mesh analysis? Is it clear for everyone? Any doubts in this topic? If it is clear, I will move to nodal analysis. The next topic is the nodal analysis. Is it clear for everyone? Please respond. Everybody solve the problems? Yeah, okay. So I will move to the next topic, that is, so far we have used the mesh analysis to solve the network for finding out the currents, different mesh currents. Now the dual to this mesh analysis, the dual is a nodal analysis. So that means here we used the loops. In the mesh analysis, we used the loops to find out the currents. In nodal analysis, as this says nodal, we use the nodes. We use the nodes and we apply KCL. In place of KVL, we use KCL to find out the node voltages. Okay. So only simply it is a dual for mesh analysis. In mesh, so I will tell you the nodal. So put the heading, this write down the nodal analysis. Already we have discussed when the nodal analysis is applied and when the mesh analysis is applied in solving the circuits. If the circuit is having more number of voltage sources and if you want to find the mesh currents, we will use mesh analysis. And if circuit consists of current sources, more number of current sources, and if you want to find the node voltages, if in order to find the node voltages, then we will use nodal analysis, right? So in mesh analysis, we find out we applied the KVL for each loop. Loops are used or mesh are used to apply the KVL and currents, loop currents are found. So as in nodal analysis, for nodes, instead of loops, here we use at the nodes, we will apply KCL and we will find out the node voltages. Okay, that is the difference between these two mesh analysis. Here KVL, in nodal analysis, we use KCL. So we will take the loops as the reference or mesh as the reference in mesh analysis. In nodal analysis, we will take the nodes and we will apply KCL at the nodes and we will evaluate the node voltages. So from that we can find the currents as well. We can find out the currents also. Okay. So once if you finish this nodal analysis also, circuit is given, you will use. So by seeing the circuit itself, so you can use any of these analysis techniques and you will automatically, you will get the idea to solve the problem, right? So now I will show you one circuit and one example how to apply the nodal analysis. To write down this, note down this circuit. Note it down, this circuit. So here one current source is there with the current I. So how many nodes are present in this circuit? How many nodes are there? Anyone from the class? How many nodes? See, this is one node. I will write this node as A, and this is one more node. This is as B. And see here the downwards, all these points are common node. This is a common node. So usually we will take a reference node. We will assume that that is at a zero potential. That means nothing but ground. So that is the first point we need to follow in a nodal analysis. We will assume one node, so which is a reference node. That means where the voltage is equals to 0. And first identify the nodes. What are the nodes? Here we identified one node A, one is at A and another node is B. Okay. So assume some current is flowing in this direction, that is I, or we are applying since the node analysis. So assume the voltage. The voltage at this node 1 is V1. Since it is a node 1, or VA, we will assume VA with reference to the ground. Okay, that means this is at positive potential. Assume the ground node is at negative potential. Similarly, here the voltage at node B, okay, is V2. As we applied the currents, we assumed the currents in mesh analysis. Here we will assume the voltages in nodal analysis, right? Is it clear? So that is the first step to be followed. Take a reference node. So just for our reference purpose, because so we are calculating, that means to find out the voltage, to assume the voltages. See, that means V1 is the voltage at node 1. But what is the voltage? Voltage is nothing but potential difference between 2 points. So what is the other point? Other point is the reference node. Okay, that means with respect to the reference node, the voltage at node A is V1. Is it clear? Is it clear for everyone? Voltage means we need to define the voltage between 2 points, potential difference between the 2 points, right? So here the 2 points, suppose if you assume node A, voltage at node A is V1. So that is the voltage between node A and the reference node, right? Similarly, at node B, the voltage is V2, that is with reference to the again reference node. Voltage at B, voltage at the point B with reference to the reference node. Now we will write the KCL equations. First, let us assume at node A. At node A, write the KCL equation at node A. So assume the currents, leaving currents, and assume the current is flowing in this direction, and here one more current I1, and this is approaching I1. This is I. Already I is given. Okay, I is given. Okay, so how to write this one? KCL equation at node 1, that is node A. Simple. KCL, sum of leaving currents is equals to sum of entering currents. I is equals to
I1 plus I2.
So, but here we are not writing in terms of the currents I1. So I want to write this in terms of voltages, because we are using nodal analysis to find the node voltages, right? So what is the voltage at V1 with respect to the reference potential? So that we need to write in terms of, so what is I1 here? I1 is V1 by
R1.
Yes, right. V1 by R1. Because so voltage at node A with reference to the ground node, that is this bottom node, because current is flowing in this direction. So V1 is the potential at A, and the ground is at 0. Ground is at 0 potential. So V1 by R1 is the I1. So plus with reference to A with reference to B. Another current I2 is flowing towards B, right? Towards B. So what is the voltage between these two? We can write the voltage difference V1 minus V2 by I2. V1 minus V2 by, sorry, R2, not I2, R2. V1 minus V2 by R2 is I2, right? Because here, so I2 is flowing from node A to node B. At node A, voltage is V1, and at node B, voltage is V2. So the voltage difference V1 minus V2 by R2 is I2 here. Okay, so I is equals to, we are writing KCL only, but in terms of voltages. So at node A, the entering current is I. So I is equals to leaving current I1, and one more leaving current is I2. I equals to I1 plus I2. I1 is V1 by R1. I2 is V1 minus V2 by R2. So this is the first equation. So by applying the KCL at node A, we got the first equation. Is it clear? Or shall I repeat this one? Is it clear for everyone? Any doubt in writing this equation? Simply it is a KCL. That means sum of entering currents is equals to the sum of leaving currents. And if you see the node A, there are three currents. I is entering from the source, I1 flowing through R1, I2 flowing through R2. So already we assumed the voltage at node A is V1, voltage at node B is V2. So entering current I is equals to leaving currents I1 plus I2. So in terms of node voltages, we have written I1 as V1 by R1, I2 is V1 minus V2 by R2, right? So now apply KCL again at node B. At node B. Okay. At node B. Write the KCL at node B. Tell me what is the KCL at node B. Assume the current. Assume the remaining here, one more current here and one more here. Or you take reference as V2 here. V2. So tell me the KCL equation at V2. How to write the KCL at V2?
I2 is equal.
Now if we write I2 here, since we are writing with reference to the B, again, so this becomes V1 minus V2 only approaching. Suppose if you write this as in this direction, if you consider the current is in this direction. So now how to write this one? The current is with reference to node B.
V2 minus V1.
V2, right. V2 minus V1 by R2. V2 minus V1 by R2 plus V2 by R3. V2 by R3, this current. Then again, one more. V2 by, what is the current? These two are in series. R4 and R5 are in series. Right? Or this you can write as V1 minus V2, the same old minus of. So we can write this becomes a minus of V1 minus V2 by R2. It will. Both are same. Okay. So, but with reference to B, so I am writing the V2 as a reference voltage. So I am taking V2 minus V1, assuming the current is also leaving here, V2 minus V1 by R2. So all are leaving only here. All are leaving currents only. Yes, any doubt in this? Is it clear? The second equation. The only thing is reference. What is the reference voltage I am taking? Okay, for second node I am taking V2 as the reference. V2 as reference. So I2, I am writing, you can write I2 as V1 minus V2 by, now it becomes V1 minus V2 by R2 is equals to sum of these two currents. That means this term will become negative. So both are same or not? Sivanageshwara, what is this? What is your doubt?
Nothing, sir.
Is it clear?
Yes, sir.
No, you send a message that no, sir.
అది నో డౌట్ అని చెప్పాను.
Okay, right. Okay, so both are same. Even if you write I2, if you have any confusion in writing like this, you can take this one I2 also same as entering, remaining 2 as leaving. Otherwise, you follow this procedure only. Okay, this is easy because we are taking B as reference. So at node B, with respect to B, we have to write. So V2 minus V1 by R2 means it is leaving. So V2 by R4 and R5 are in series. So R4 plus R5, V2 by R3. So all are this summation is equals to 0. So now we can simplify this as I is equals to V1 into 1 by R1 plus V1 into 1 by R2 minus V2 by R2, first equation. So that means in terms of V1, we will get 1 by R1 plus 1 by R2 minus V2 into 1 by R2 is equals to I. So that means two unknowns, no two node voltages, V1 and V2. In terms of V1 and V2, we have written the first equation. Similarly, simplify the second equation, V2 by R2 minus V1 by R2 plus V2 by R3 plus V2 by R4 plus R5. So V1 minus V1 into 1 by R1 plus V2 into 1 by R2 plus 1 by R3 plus 1 by R4 plus R5 is equals to 0. Again, two equations. So in terms of two unknowns, here the unknowns are node voltages. Here the unknowns are the node voltages. One node voltage V1, the second node voltage so from this we can find all the currents also. So from this we can find I1 is V1 by R1. So if you know the V1 and R1 is given, circuit also, right? Shall we go for a Is it clear for everyone how to apply the nodal analysis? Yes or no? Shall we? Is it clear? Is it audible?
Yes, sir.
Yeah, okay. Now we will solve a problem. Circuit, one circuit. 10 ohm, 3 ohm, 5 ohm, which is same as I have taken in this example. The same kind of okay. So find the voltages, node voltages and loop currents. Node voltages and currents in the given circuit. So first take the reference nodes. One reference node, bottom node as a reference, and two nodes where the voltages, we need to find the voltages. How many nodes are there in the circuit? Which is same as our example problem. Okay, take the reference nodes. Two nodes. This is A or node 1 where the voltage is V1, and one more node 2 where voltage is V2. Right? Now write the equations. Write the KCL equation. Yes, tell me what is the first one? KCL at node 1. What is the first equation?
5 is equal
5 is equals to, yes, V1 by 10.
yes, sir.
V1 by 10 plus V1 minus
V1
V2
minus
by
V2 by
3.
3.
Yes, right. V1 minus V2 by 3. So simplify this. V1. What are the coefficients for V1? 1 by 10 plus 1 by 3 minus V2 by 3 is equals to 5. So this is first equation. Next, write KCL at second node. KCL at second node. V2 minus V1 by 3
3.
plus V2 by
5.
5
5.
plus
V2 by 1 plus 10.
no, see,
Minus
1
1 minus
is the
10.
resistor, 10 volts is the voltage source, that is voltage source. V2 minus 10 volts by 1, that is voltage source, not a resistor, right?
Yes, sir. Yes, sir.
Yeah. Is it clear? Here 10 volts is not resistor, it is a source. Voltage, that is also a voltage source. So voltage, right? Okay. Since that is a voltage source. So V2 by 3 minus V1 by 3 plus V2 by 5 plus V2 is equals to 10. 10. So V1 coefficients minus 1 by 3, only minus 1 by 3 plus V2. V2 coefficients is 1 by 3 plus 1 by 5 plus 1 is equals to 10. So this is second equation. So solve these two equations. First write the coefficient. Second, so 1 by 10 is 0.1 plus 1 by 0.1 plus 1 divided by 3. 0.43 V1 minus 0.33 V2 is equals to 5. This is the first equation. Minus 0.33 V1 plus 1 divided by 3. 0.33 1 divided by 5. 0.2 plus 0.33. 0.606 plus 1. 1.606. 1.606 V2 is equals to 10. So solve these two. Everybody should have the calculators, please. Should keep a calculator with you for every class. Solve this one. What is V1? What is V1? Anybody got the answers? So solve these two equations. V1, you get V1 as 19.85 volts and V2 is 10.9 volts. V2 is 10.9. Now find all the currents. Now find all the currents. Assume the currents. So here the current flowing through I3, I1, 3 ohms is I3 and this is I10, and similarly here I1, this is I5. Like that you find all the currents. How to find the currents? If you assume I3 is flowing through 3 ohms in this direction, so you can write I3 as, what is the expression for I3? How to write I3? If I show the direction, reference direction as from node V1 to V2, I3 is V1 minus V2 by 3. V1 minus V2 by 3 ohms. I3 is V1 minus V2 by 3 ohms. I5 is V2 by 5. I5 is V2 by 5. I10 is V1 by 10.
V1 by 10.
Yes, I10 is V1 by 10. What about I1? I1 is V2 minus 10 volts by 1. I1 is V2 minus 10 by 1. Okay, these are the 1, 2, 3, 4 currents. So 4 currents, you know V1 value and V2. So you can evaluate all the currents in the circuit, right? Okay, so like this, similar to the analysis, that means whatever analysis we have used. So there are three more, that means like here two reference nodes are there. Like that, three reference, you will come across three reference, whatever we solved in like in mesh analysis. So in mesh, we solved two unknown problems like that, three unknown problems like that we solved, right? So similarly, here also, so after that there are three unknown problems will be there. Three are there. So we will go for that problem in next class, right? Which are having three nodes. So there again you need to apply the Cramer's rule to find three unknown voltages. And if you know the voltages, as in this problem we have evaluated the currents, you can find the currents also, right? Right? Don't leave the class. I will take the attendance. I will stop recording and I will take the attendance. Yes, respond to your